Heat transfer in building envelopes occurs through conduction, convection, and radiation. Insulation materials minimize these by trapping gases within a solid matrix. Air has a thermal conductivity of approximately 0.026 watts per meter Kelvin, but convection currents within large air gaps would transfer significant energy. By dividing the space into microscopic cells or pores, insulation suppresses this convection. The solid framework of the material itself contributes to conduction, while the cell walls and fibers act as shields against thermal radiation. The effectiveness of any insulation is quantified by its lambda value, where lower numbers indicate superior resistance. Most common rigid foams and fibers achieve values between 0.030 and 0.045. Selecting the right material requires balancing this thermal resistance with mechanical properties and moisture behavior under specific environmental loads. Expanded polystyrene, or EPS, begins as small resin beads containing a blowing agent, typically pentane. When exposed to steam, these beads expand up to 50 times their original volume, forming a closed cell structure. These expanded beads are then molded into large blocks or specific shapes using heat and pressure, which fuses the beads together. This process creates a material that is 98% air. Because the beads are fused rather than being a single continuous solid, tiny interstitial gaps exist between the spherical boundaries. These gaps allow for a degree of water vapor breathability, but they also mean the material can absorb liquid water through capillary action if submerged over long periods. EPS is highly versatile due to its adjustable density, which directly correlates with its compressive strength and thermal performance across various construction applications.
Extruded polystyrene, known as XPS, is manufactured through a continuous extrusion process. Molten polystyrene is mixed with a blowing agent and forced through a die, where it expands into a dense, rigid foam. Unlike the fused beads of EPS, XPS possesses a completely uniform closed cell structure with no voids between cells. This lack of interstitial space results in exceptional resistance to water absorption and high water vapor diffusion resistance. XPS typically exhibits higher compressive strength than standard EPS, making it the primary choice for inverted roofs and perimeter insulation where the material is in direct contact with soil and groundwater. Its smooth, skin-like surface and high density provide a robust barrier against mechanical loads. However, the manufacturing process is more energy-intensive, and the choice of blowing agents historically impacted its environmental footprint compared to simpler expansion methods. Mineral wool, encompassing both glass and stone wool, functions through a completely different physical principle than plastic foams. It is produced by spinning molten glass or volcanic rock into fine fibers, which are then bonded with a thermosetting resin. This creates an open-cell fibrous matrix that excels at trapping air while remaining highly permeable to water vapor. The random orientation of these fibers provide excellent acoustic dampening properties, as sound waves are dissipated into heat through friction within the dense fiber network. Unlike polystyrene, mineral wool is non-combustible, typically holding an A1 fire classification, and can withstand temperatures exceeding 1000 degrees Celsius. This makes it indispensable for fire-rated assemblies and ventilated facades. While its thermal conductivity is comparable to EPS, its ability to remain dimensionally stable under extreme heat sets it apart in high-risk structural applications.
Compressive strength is a critical differentiator when insulation must support structural loads. XPS is categorized by its ability to withstand high pressure, with grades often rated at 300, 500, or even 700 kilopascals at 10% deformation. This allows it to be placed under concrete floor slabs or in heavy-duty parking decks. EPS also offers load-bearing variants, but generally requires higher densities to match the performance of XPS. Mineral wool is comparatively soft in its flexible batt form, but high-density boards are engineered for flat roof applications where foot traffic is expected. In these boards, the fibers are often oriented vertically or compressed into layers to increase point load resistance. When designing for load-bearing scenarios, engineers must account for long-term creep, which is the gradual deformation of the material under a constant load over decades of service life. The movement of water vapor through a building assembly is governed by the mu value, or water vapor diffusion resistance factor. Mineral wool has a mu value of approximately 1, meaning it is as permeable as still air. This allows moisture to move freely through the wall, which is essential for drying out construction moisture in timber frames. EPS has a mu value typically between 30 and 70, providing moderate resistance. XPS is much more restrictive, with values often exceeding 100. In cold climates, placing a high-resistance material like XPS on the exterior can trap moisture inside the wall assembly, leading to interstitial condensation. Conversely, in wet environments or below-grade applications, the low permeability of XPS prevents the insulation from becoming waterlogged, which would otherwise destroy its thermal resistance. Understanding these coefficients is vital for high-growth thermal modeling and preventing structural rot.
Fire performance is where the distinction between organic polymers and inorganic minerals is most stark. EPS and XPS are thermoplastic materials, meaning they melt and can contribute to flame spread if not treated with flame retardants. Most construction-grade polystyrenes are classified as Class E under European standards. They must be protected by fire barriers, such as gypsum board or thick render, to prevent ignition during a fire event. Mineral wool is naturally inorganic and does not support combustion. It acts as a fire stop, preventing the passage of flames and heat through wall cavities. In high-rise buildings, regulations often mandate the use of mineral wool for the entire facade, or at least as horizontal fire breaks between floors, to stop the chimney effect. Choosing between these materials often involves a trade-off between the superior moisture resistance of plastics and the superior fire safety of mineral fibers. Selecting insulation depends on the specific stressors of the application zone. For perimeter insulation below the frost line, XPS is the technical standard due to its zero capillarity and high compressive strength. In standard external thermal insulation composite systems, EPS is frequently used because it is cost-effective, easy to cut, and provides a stable substrate for thin-coat renders. For ventilated facades, where fire safety and breathability are paramount, mineral wool is the preferred material. In flat roof construction, the choice depends on the buildup. An inverted roof, where the insulation sits above the waterproof membrane, requires the water resistance of XPS. A warm roof buildup, where the membrane is on top, can utilize mineral wool or EPS. Each decision must weigh thermal efficiency against the risk of moisture accumulation, fire spread, and the mechanical requirements of the specific building component.
The theoretical performance of insulation is often undermined by poor installation. Thermal bridging occurs where gaps between boards or structural penetrations allow heat to bypass the insulation layer. Rigid boards like EPS and XPS require precise cutting and are often manufactured with shiplap or tongue-and-groove edges to ensure a continuous thermal envelope. Any gaps larger than a few millimeters should be filled with expanding foam to prevent convective heat loss. Mineral wool, being flexible, can be friction-fitted between studs, filling voids more effectively in irregular spaces. However, it must be protected from wind wash, where cold air penetrates the fiber matrix and reduces its effective R value. In all cases, the continuity of the insulation layer is as important as the material's lambda value. 1% of uninsulated area can lead to a disproportionate 30% increase in total heat loss through a wall. Evaluating the environmental impact of insulation requires looking beyond the raw material. Mineral wool is made from abundant natural rock or recycled glass, but requires significant energy for the melting process. Polystyrenes are derived from crude oil, making them susceptible to price fluctuations in the petrochemical market. However, their lightweight nature reduces transport emissions. EPS is widely recyclable if collected without contamination, whereas XPS recycling is more complex due to the potential presence of older blowing agents. The most significant environmental benefit of any high-quality insulation is the massive reduction in operational energy over the building's 60-year lifespan. This carbon offset usually far outweighs the embodied energy of the material itself within the first few years of use. Future developments focus on bio-based binders for mineral wool and carbon-neutral production pathways for polymer foams to further improve the life cycle assessment of the building stock.